Today's topic is Maxwell's equations of electrodynamics or what we call electricity and magnetism. And in this class, we shall write down the Maxwell's equations of electrodynamics in SI system as well as in Gaussian system. The subject of electrodynamics or electricity and magnetism rests upon four pillars. In other words, there are four basic laws or equations. The entire subject can be described, can be elaborated, can be explained with the help of these four basic laws or equations, which are called Maxwell's equations of electrodynamics, called Maxwell's equations. In this class, we will not derive Maxwell's equations, we will not explain them, or we will not mention their utility. Those will be discussed separately. In this class, we will just write down these Maxwell's equations in two systems of units. One is system internationally or the SI system of units, and the other one is the Gaussian system of units. First, the first Maxwell's equation. In SI system, it is divergence of vector E is equal to rho by epsilon 0, and this is the differential form of first Maxwell's equation. Differential because this equation involves derivatives like del del x, del del y, del del z. Here vector E stands for electric field vector, a fundamental vector of electrodynamics. Here rho stands for the total charge density, so rho is also called rho total. And total charge density is the sum of two terms. One is rho f, where rho f stands for free charge density, and rho p stands for polarization charge density. which is related to the polarization vector through this relation, where vector P is the polarization vector or often simply called polarization, and epsilon 0 is the permittivity of vacuum or free space. We can alternately write the first Maxwell's equation as follows. Divergence of vector E is equal to rho f by epsilon. This can alternately be written as divergence of vector D is equal to rho f, where epsilon is permittivity of a medium which is polarized due to an electric field, and the two are related as where Ke is the dielectric constant of the medium, and vector D is called the displacement vector. And is related to the electric field and polarization through this equation in SI unit. And here vector P, which represents polarization, is defined as number of electric dipole moments per unit volume. Now what we have mentioned here is the differential form of first Maxwell's equation. In integral form, Maxwell's first equation has the following form. And this is also referred to as Gauss' law of electrostatics. Integral form because this equation involves integration over space. That is over x, y, z, where Q represents the total charge, and hence it is also called Q total. Total charge that is enclosed by S, which is a closed surface. And this Q consists of two parts. One is QF and the other one can be written as QP, where QF is the total free charge and QP is the total polarization charge. And here vector ds is a surface element, a typical surface element of the closed surface S, and it encloses a volume, say capital V, and therefore we can write, instead of Q, rho dV over V. QF is integration rho F dV over V, and QP is integration rho P, the integration being over the volume V. And alternately we can express this integral form, that is, as the closed surface integration over vector D, which is the electric displacement vector. It is equal to the total free charge, and this is the Gauss law in dielectric. So this is the differential form of first Maxwell's equation. This is the integral form of the first Maxwell's equation, it being also called Gauss law of electrostatics. And these are first Maxwell's equations expressed in SI unit. Let us now write down the first Maxwell's equation in Gaussian unit or Gaussian system, and it is divergence equal to 4 pi rho, and this is the differential form, and the integral form in Gaussian system will be four pi q. We next discuss the second Maxwell's equation, first in SI system and then in Gaussian system. Now the second Maxwell's equation in SI system. According to second Maxwell's equation, divergence of B equal to 0. And this is the differential form where vector B is the magnetic induction vector, and the integral form is the closed surface integration of magnetic induction, that is the flux of vector B over a closed surface, is 0. Here S represents closed surface in the B field, and this is referred to as Gauss law of magnetostatics. So the second Maxwell's equation in SI system is this one in differential form and this one in the integral form. And let us write down their counterparts in Gaussian system. And it is the same. So divergence B equal to 0. This is the differential form. And the flux of B across a closed surface is 0. This is the integral form. Let us now move over to the third Maxwell's equation. We now write down the third Maxwell's equation. And it is curl of vector E is minus del del t of vector B, which is the differential form where t is time. Other symbols have been defined earlier. Let us now mention the integral form, which is the circulation of the electric field vector over a closed contour C This is negative of the time derivative of the flux of B over the open surface S that is enclosed by the contour C. Where C is a closed contour enclosing open surface S. Now this tangential line integral of the electric field vector, which is also called the circulation of the electric field vector over the contour C, is referred to as the electromotive force E. So E is equal to this is called EMF or electromotive force, and this open surface integration of the magnetic induction vector B, let us call it phi m, which is defined as magnetic flux. So this is the flux of B over the open surface S. In view of these definitions, let us rewrite this integral form as which is the famous Faraday's law of electromagnetic induction. So third Maxwell's equation in differential form is this one, and in integral form it is this one, where the integrals are occurring within E and phi m. It is also evident from this expression that variation of B gives rise to an electric field, and that is what Faraday's law of electromagnetic induction says. So in a nutshell, it says that a varying B produces E. We now write down the third Maxwell's equation in Gaussian system. So third Maxwell's equation in Gaussian system will be curl E equal to minus 1 by C del B del T, differential form, and in integral form it is where c is the speed of light in free space, which is 3 into 10 to the power 8 meter per second. We now move on to the fourth Maxwell's equation in SI system. The differential form is curl of magnetic induction B is mu 0 times vector J plus epsilon 0 del T of the electric field vector E. Where mu 0 is the permeability of vacuum and vector J represents, we can also call it J total current density. And it has three parts. Where vector Jf also can be expressed as sigma vector E is the conduction current density or free current density or true current density. And sigma is the conductivity of a medium. Vector Jm represents the magnetization current density, whose expression is curl of M, and vector M represents the magnetization vector, or simply called magnetization, which is the magnetic dipole moment per unit volume, small m being the magnetic dipole moment and capital M representing magnetization. And vector Jp represents the polarization current density, and this is its expression. And let us mention that all of them, that is vector Jf, vector Jm and vector Jp, involves electron transport or electronic movement, that is physical movement of electron. For instance, Jf corresponds to free movement of electron, say electron running or moving along a wire. Vector Jm, whose expression is curl M, represents movement of electron in a closed loop. Also called Amperian loop. And vector Jp, whose expression is dp dt, p for polarization, involves movement or oscillation of electron or charges of a dipole. So J of the right hand side of this fourth Maxwell equation corresponds to physical movement of electron, and this term can be written as it is called vacuum displacement current. Density, and is not linked to, that is, does not involve any electron movement, and it corresponds to variation of E with time that generates a B field, and this is Maxwell's concept. So variation of E generates B, and hence it is called current density. In other words, there are two types of currents, one involving electronic movement, the other one corresponds to no electronic movement, but there is variation of electric field vector. Alternately, this fourth Maxwell equation can be expressed as, so let us write here alternate form, which is and there is another alternate form, which is curl of H equal to Jf plus del d del t, where mu represents permeability of medium. And the vector h stands for vector b by mu 0 minus vector m, where b is magnetic induction and m is magnetization, and this vector h is called magnetic field. Having written down the differential form of fourth Maxwell's equation, let us now write down the integral form, which is the circulation of the magnetic induction over a closed contour C is equal to mu 0 times and this can also be written as mu 0 times I. Here I is actually I total because it corresponds to vector j, which is actually j total, and this I is actually I vacuum displacement current, because this term involves this factor, which is actually the vacuum displacement current density. So this is the integral form and is referred to as Ampere's circuital law plus Maxwell's contribution. According to which a varying electric field generates a B field, that is current, and hence this factor is called vacuum displacement current density. Let us write down the alternate forms of this integral form, which is and this term corresponds to free current density, so it will be free current, and this one is called displacement current. We have to be careful while writing because this I is the total current, this IF is the free current, this is vacuum displacement current corresponding to del del T of epsilon 0 vector E, while ID represents displacement current, which corresponds to del del T of vector D, which is actually so in addition to this factor, it includes vector P also. So this is free current and this is displacement current. So the fourth Maxwell's equation is this one, which is the differential form, and this equation which represents the integral form. We now write them in Gaussian system. So fourth Maxwell's equation in Gaussian system, which is curl B equal to 4 pi by C into vector J plus 1 by C del T of vector E. This is the differential form, and this is the integral form. Let us now make a gist, that is, write all the equations at one place. Here we shall write the SI equations, and here let us write the Gaussian equations. The first equation in SI system, it is divergence of E equal to rho by epsilon 0, and in Gaussian system it is divergence E equal to 4 pi rho. The second equation is same whatever system we use, so it is divergence B equal to 0 in both. Now the third equation, which is curl of vector E is equal to minus del B del T, and here it is curl of E is minus 1 by C del B del T. And finally the fourth equation, according to which curl B is mu 0 vector J plus epsilon 0 del T of E, and here so these are the set of Maxwell's equations in SI system and Gaussian system. In separate video we shall derive them, we shall explain them, we shall discuss their significance or importance. In separate video we shall mention application of these equations which are of paramount importance in electricity and magnetism.